is Junichiro Horikawa, and this is the 12th episode of VEX for Algorithmic Design, and today's topic is vector basics. In today's session, I'm going to talk about what vector is, and then show you some simple vector operations like addition, subtraction, multiplication, division, which you have already been using it from previous episodes, but we're going to strengthen what it really means. I'm gonna get into a bit more advanced topic for vector, which is a dot product and cross product, what they are and how you can use them for your purposes. I'm going to give you a little bit of exercise for all these things that we're going to learn. Now let's start by looking at the definition of the vector. A vector is a information which has the direction together with the length of its direction. So having those two information, you'll be able to create a vector, and it often's being displayed or expressed as x, y, z if it's 3D vectors. If it's 2D vectors, it is written like x and y. So when we say vector operations, it means to transform this vector, this direction with the length, to another direction with another length. There are several benefits having this data type. One is you can use this vector or directional value in order to move stuff from one point to another. So let's say you have a sphere like here, and you want to move this sphere to this direction. In this case, using a vector would be able to move this sphere pretty easily. It's just by, if the position of the sphere is called P, then the vector is called V. In this case, the moved position of this new sphere is actually equal to P plus B. And I am going to explain that in detail while we touch through VEX code. As I say, since it is drawn, it is often visualized as an arrow which have a direction with the length. It is often used in 3D space in order to use it for a transformation like translation, scaling, and rotation. But you can also use this vector value for other purposes as well. Especially in Houdini, you also use this vector for colors. In this case, it's all GB. And this has 3 values, and only because so, Houdini is using vector values in order to control the color value. So in some case, vector is not used for direction and size like the colors, but when it comes to deal with inside a 3D space and one says vector, then most of the case it means the direction and size, and you often draw it with an arrow. Now let's think about in a 2D space, and let's say the horizontal axis is x and vertical axis is y, and you have some vectors inside this space. Let's say v. And the coordinate or the value of this v value, the vector value, is say x prime and y prime. This means is that when you project the x coordinate to the x-axis and y coordinate to the y-axis, the y coordinate is equal to y prime and x coordinate is all called x prime, right? Now when we talk about vectors as a direction and the size, the starting point of the vector is always 0, 0. But as you might have noticed, and for some vector values, you don't really need to have this directional or size value in some cases, such as a point position of a geometry. let's say you have a sphere which is constructed by many points, and each of the point has its own position. Let's say P prime. Now this P prime is also described as a 3D vector, x, y, and z. But in order to define the position, you don't really need it to be a vector value, I mean the directional value, or to have a size. You just need to, this coordinate just describes where it is, and that's all. You don't really need the arrow information in order to define where the point is. But pretty much, I mean, the basic concept is the same. You can also use those position as a vector as well if you want, but remember that if the coordinate or the origin of the 3D space is right here on the 0, 0, 0, then the vector of this P, if you want to use this P as a direction value, then you always get the arrows from 0 to this point. So that's why you need to be careful of when you want to use those position value as a directional value. Now enough with the sketches, let's try to actually use them with a simple operations in Houdini together with the VEX. First thing we like to try is the vector addition and subtraction, which we have already used this a lot of times with previous episodes, but I'm going to explain a little bit deeper how this addition and subtraction works for vectors. Okay, so let's start by creating a single point now using add. First of all, let's create a geometry node and create an add node with a single point. And first I'm going to try with the addition. So let's create a point wrangle and do some really simple addition calculation. So let's name this vector addition, and let's create two random vectors named as b1 and b2. So the first one b1 set 1.0 for the x, to 0.5 for the y, and 0.0 for z. Vector b2 is set, let's say 0.0 for x, 1.0 for y, and 0.5 for z. Okay, and first thing I would like to do is to visualize this on a display, on a viewport, so that we can see which direction is aiming for those two vectors. So in order to do that, we first create an attribute called v1 and v2, and then store these two values to that attribute in order to visualize them. So v1, v at v1 is equal to v1, v at v2 is equal to v2. Okay, so after we have stored this attribute, in order to visualize the vectors, we're going to create a new marker using this visualization marker right here on the middle. Right click, and you click this plus button with the marker. You'll be able to create a new marker to visualize like text or vector values. We're going to choose as a vector value, and let's name this v1, v1, and style as vector, and attribute as v1. So after you have type enter and check that the v1 is checked, then you'll be able to see a attribute v1 being drawn as a line, a yellow line here, which shows the direction from the starting point to the end point going faded away from yellow to black, like this. So this is the actual direction where this v1 is heading, and we can check that by creating this marker right here. So let's do the same for the b2. So click plus marker b2, b2, attribute b2, and set it to vector for the style. I want to change the color for the second one, so let's change the color by going into the color picker and choose like cyan. We also need to change the alpha to 1. Okay, now we have two vectors being shown on a viewport. One is yellow and one is cyan. And the yellow one is the V1 and cyan one is the V2. Now it's time to try adding those two vectors and see how the result would be like. So let's create another vector V3 and let's try to add those two vectors V1 and V2 by do a simple adding operation like this. And let's also store this as V3 as an attribute. And let's also try to view that with a marker to see how it looks like. Okay, I should use the semicolon here. Okay, now go back to the marker, click plus, marker, B3, 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 and for this one let's set it to red, and also let's change the style to vector. Okay, I gotta change the color again to red with the alpha value 1. Okay, now you see that after you've changed after you have created the V3, the red vectors will be created, and you can see that now after you have shown all those three vectors, you might be able to see the relationship between the yellow cyan one and the red one. And let's try to draw the relationship for the addition in this sketch first. So first of all, we had two vectors. One is V1, one is V2. Okay, and when we added, we had a new vector, something looking like this, V3. So how does this work? The direction changed and the size also changed. Now the addition of the vector means that you can combine the direction to create a new direction with a new size. So in this case, say you started from a vector 1, like here, V1, and after this, going into this point, if you want to add a new vector, you start from this point. In this case, this V2, and V2 direction is this way, so you can add the V2 like this, and as a result you'll be able to get this combined vector. So the starting point is always the same. It all starts from here, which is 0, 0 position, or 0, 0, 0 position, and you started from 0, 0, 0 to B1, then from B1 you add this V2 to extend the vector to a different direction, and as a result you have created this new direction with new size. So that's the concept of vector addition. So the benefit of using this vector addition, you'll be able to change the direction based on the different types or different kinds of directional values and sizes, and it often used for translation or transformation related stuff for geometrical modification. Now let's try to see the changes by changing those values for V1 and V2. If I set the Z value for V1 to 1, you see that something has just changed. If I set this X value to -1, the yellow arrow changed and the red one also changes, but in any way you'll be able to see an added vector for yellow and blue for the V3 for the red one. So even if you have changed the yellow one to other direction, you still add this blue one, the cyan one, and as a result you'll be able to get the combined vector values like this. So it seems pretty simple, but it is one of the most important concepts of the vector. When it comes to deal with more complex one, the addition of the vector comes at any places, so try to visualize this anytime you are adding vectors together. Now let's try to do a subtraction as well. The subtraction is pretty much the same with the addition. It's just the addition of a negative value, so it's pretty much the same, but let's try to see it. So vector subtraction, and let's have two similar vector values here, and let's keep these as well. And for the v3, I'm going to say v1 minus v2. Let's see the difference. Now the direction and the size has changed from the previous addition, and let's see why. In this case, we had v1 in this direction and v2 in this direction, and what we were doing is to first have this v1 from 0, 0, okay, 0, 0, 0. And from this point, the end point of the v1, we are subtracting this v2. Subtracting meaning is to go to the other direction of v2, meaning if this is the positive direction, then the negative direction is this way. Okay, so this is, okay, so this is a negative v2. So this is the result of the subtracting. As a result, the final combined vector is from 0, 0, 0 to the endpoint of two combined vector, which is v3, and which is the v3 value that we also get inside Houdini, this red line. So that's how the subtraction works. Pretty simple. It's pretty much similar to addition. It's a bit more hard to imagine than the addition itself, but if you just carefully try to visualize it, it's pretty straightforward. Now that we have some idea about addition and subtraction for the vectors, let's try to do some little exercise in order to see how we can use those addition and subtraction in real practice. Okay, so we're going to start by dealing how we can move the geometry point with specific vectors. So let's say we want to move the points of this sphere. Let's try to change this to polygon and to have several vertices on a surface. Then first thing I would like to do is to create a vector in order to use it for a translation, for moving the point. So let's try to create a point attribute to each of the point first. Let's call this init1, and let's create a vector value, vector v1 is, let's create the parameter for the vectors using chv function and say translate. And store this value to a v1 attribute like this. Let's promote the channel so that you can create your own vector value for each of the point. And as right now I'm showing the marker for v1, so the attribute that I've stored as v1 is showing as a yellow line right this. The next thing I would like to do is to move each of the point using this vector to this direction with this size. Okay, so let's do this using another wrangle. Let's give another point wrangle and connect with init1. And if you look at the geometry spreadsheet, let's go to open up the geometry spreadsheet to check the point attribute, and there you'll be able to see each of the point has this new attribute called v1, and that is this yellow direction with the size. And we want to use this directional vector value in order to move each of the point to that direction. And in order to do that, we can use this new point wrangle. Let's call this move1. And first of all, let's try to access the point position of this sphere for each of the spheres. So we can access to that by accessing to a p attribute, capital P attribute. And then what we can do here now is to change this position with a vector value stored in a v1 attribute. So to update the position value, we can say position plus equal with a v at v1. Okay, at this point the point position doesn't really change because we need to access to this at p in order to update. So let's try to update the capital P with the updated position and see what happens. And the point position, each of the point position has changed to a new position, and seems like every geometry, every sphere, the whole geometry has been changed, has been moved to the same direction with the same size. Well, that is because I am using just one single vector for all the points. Okay, so that's the result, and let's see how it's being moved by also showing this the init value as the blue flag and this one as a template flag, so that we can see the wireframe like this. Now, as you can see, if you follow the yellow vector line, you can actually see that the moved point is connected with this yellow line. So you can assume that the yellow line has been used to move each of the original point to the new positions. And if you change those vector value, you'll be able to change the vector value together with the moving place, the moving position of each of the point. So that's one of the most used case for vector addition to change the point position of specific geometry, like in this case a sphere. Now, if you try to think about this in detail in Sketch, let's say let's think about in 2D. This is the point on a surface, let's say this is P, and you have a vector, let's say from 0, 0 to, let's say -1 and 1, like this. And you want to move this point using this vector v. In this case, the point can be described as a new vector, which is something like this. So ax prime, y prime, this. And you can consider this p as a x prime, y prime vector to the vectors, and adding this new vector means to add a vector to this point like this. And as a result, you get a new vector values at this point, and by using this point as a new point position, this means you are translating this position to a new position. So that's how translation works in order to move the point from one point to another point using vector. Now let's also try to deal with the subtraction and with an example. This time I'm going to create another point wrangle for this sphere. Okay, and this time I'm going to create a v1 using a random function with a current point position as a seed value, which should create a random vector value. So let's try to visualize this first to see how the direction goes. And you can see that the direction is random and the size is random indeed, but there are some orientation it has, and if you look at carefully, the x and y and z value never goes negative in this case. If you look at the geometry spreadsheet for a v1, every value for x, y, and z is positive in between 0 and 1. So when we want to have all these goes anywhere in the 3D space, including negative coordinates, then we might need to do some subtraction to this original vector created using random. So let's try to do that. And since we have the random values between 0 to 1, if we could subtract each of the coordinate by 0.5, then the result of the value that we could get might be from minus 0.5 to positive 0.5. So let's try that out. So in order to do that, we're going to create a new vector value, which x and y and z is all 0.5. This. Let's also have this applied as an attribute as v2 to see how it looks like. So it is going only one direction like this. Okay. Now what we want to do now is to calculate the subtraction between those two vectors, v1 and v2, and let's see how it looks like. So the new vector v3 is v1 minus subtract by v2, and let's visualize this in as v3 attribute, see how it looks like. Now the red arrows or red direction or red vector is showing more randomized direction, since it can use a negative value for both every x, y, and z, and also a positive value at the same time. So all those value becomes more randomish in 3D space. Now let's try to use this new v3 value, the randomized v3 value, to move those each of the point. So let's name this init2, and let's create another point, triangle, and let's name this move2 to move each of the point with this red arrow. So in this case, we're going to do what we have just done to move the point, axis to the point, and I'm just gonna directly move this by saying plus equal v at 3. Oops. Plus equal v at v3. Okay, and let's also hide the markers, and as you can see, each of the point has been moved randomly to the random direction with random size. If we say v1, the initial random values just go to one direction like this and goes off the center, since every point is oriented towards a similar direction. If it's v2, it's just a offset. It's just an offset moving because every direction is aiming at the same direction and same size. But by subtracting all those two values together, we'll be able to have more diverse randomized vector going anywhere for each point. So that's one trick you could use for a lot of times. I use this trick a lot of times as well myself when I want to create random vector values. Now there is one of the features you want to remember about the subtraction of the vectors, which is pretty useful to remember. So let me show you what it is. Let me first write and draw our sketch. Let's say you have 2 points in a space, in a 3D space, and if you want to create a vector directional values from A to B, what will be the best option? Like, how would it be able to create this A to B vectors? Now the answer is to subtract B with A, meaning let's say the final vector is called V, then B is equal to B minus A. So this is the equation in order to get this vector between A to B. And the reason why this works is because let's say you have this x, y coordinate as well, and this is the origin, let's say 0, 0 for this, let's say this is a 2D space, right? And the vector A can be described as this arrow, and vector B can be described as this arrow, right? So B minus A means first starting from B, and for the A goes to the negative direction for this one, so going this way from this point. And at the result, you'll be able to get this vector value. And this vector value is equivalent to the vector values right here. Now, as I said, the vector value doesn't really have a point of origin. It always starts from 0, 0, even if you draw it like this at some different position. Even if you draw it like this, offset it from the center, the origin of the vector is always 0, 0. So, meaning that this vector and this vector is equivalent or equal, just the same thing, because the vector only shows the direction and the size. It doesn't really show where it starts from. So that's the reason why I'm saying that these are the same, and that's why you get this vector by subtracting B and subtracted by A. So this is a pretty useful equations you use a lot of times when we are dealing with the vector operations. So please do remember how this works and what it is mean. Okay, so let's try to visualize this. I'm going to first create a add node, 2 points with the add node. Let's check this point. Okay, and also randomize the position by changing those x, y, and z coordinate for all those 2 values. Okay, now let's try to calculate the subtraction between this one and this one. Let's say this is a value and this is v value or v vector. Okay, so to do that I'm going to use a point wrangle. Connect those 2 points and let's name this subtract. Okay, so now I'm seeing those points right here and right here. Might be a bit hard to see, so let me raise up the point size a bit bigger. Okay, now I'm using point wrangle for this one and this one, and when we use point wrangle we only can retrieve the point position when we access to add p for the first input. So in order to get the second input position, we need to use a point function in order to retrieve that. So I'm going to name the second position name as npos, using point function for second input to retrieve the point attribute. Okay, now we can do the subtraction between this point and this point. So let's say this is B and this is A. What we want to create is the vector between going from point A to point B. So this is the point B position. So in order to retrieve that vector, in order to calculate that vector, as I said, you can calculate the subtraction from point B to current point A position. Now this should be the direction that we want to use. Now let's try to store this as a B1 attribute for this point and see the marker, to show the marker how it looks like, where it aims. Okay, seems like the point that I have inputted was right here, so I think I should look at like this. Okay, so this was the second point and this was the first point, so this should be the B point, this should be the A point. Okay, now let's try to show the marker by clicking this one. As you can see, if you also try to show the wireframe of this point, you have just created the directional value going from A to B like this. So you have successfully created the directional value. Now if you want to create the line between two with this information vector value with this point information, since currently at here we only have a current point position and the directional value. So if you want to create a line connecting those 2 points, what you can do is to use a new point wrangle. Let's say line. First, create a new point at this position by calculating the new position. Vector new pos. And you can calculate the new position by first of all retrieve the current point position, which is this position, then add a vector value, this vector value, to this point position, which is v at v1, and this new position will be somewhere around here. So in order to create a new point at this point, you can use a function called addPoint with a point position, this. And if you have 2 points, then you can connect those 2 points together with a function like addPrim 0 polyline. Will create a polyline connection between points, and right now we just want to connect the first point and the second point. The first point can be accessed by first point number can be accessed by using ptnum attribute, and the new point right here is equal to npt. So as a result, we'll be able to create a line which connects A and B as a final. Okay. Now I think you have been getting used to this using vector addition and subtraction. Let's try to do another a bit more complex example and go to the next topic. So I'm going to create an add node, create it as a single point, and next I'm going to use a point wrangle to connect with the add node, and this time I will try to move the point iteratively using for loop and update the vector at each loop and try to visualize it as well. So let's first retrieve the current point position by accessing to a add p, and let's also retrieve the current point number, which is a add ptnum. Now I'm going to create a for loop you can create as much point as you want. Let's try to create 100 points now. Now I'm going to first say pt, or pt is equal to add point with a new position. And let's also create this new position, vector new pos equals to pos, right? So I want you all to check by checking the information of the node if you have added 100 more points to the original first point, and if you see 101, then you have successfully created 100 more points. Now next thing I would like to do is to move each of the point in the for loop with a new directional value in order to move the point iteratively one by one using the previous value, or using the previous point position and going to the next point position. So what I mean is to if you have a single point started like here, first thing you want to move the point somewhere to this point, and after this you want to use this new position and start the new with a new direction to create the new point, and new point, and new point, new point, or like this, to iteratively move the point using the last point position using a vector. And you'll be doing a lot of these operations when you are dealing with something like fractal shapes or iterative motions using subsolver and so on later on. So it's pretty essential thing you know how you do this, how you can do this. Okay, so let's do this. First of all, in order to do that, you need to have some directional value in order to update this new position, right? So let's do that. Okay, to do that, I'm going to create a vector called direction and use set to create x, y, and z value here. Now we're going to start it by really simple operations. We're going to set x and z for 0, and y we're going to set some parameter value, like let's say height. Okay, and promote this height value, which is in between 0 to 1. Now we have just set the directional value. What we want to do next is to add this new position, creating this new position by adding this current position plus direction. By doing it, you have just moved one point on above. Now, the next thing what you want to do is to update the position right here, the current position, with this new position, so that in the next iteration you can use this newly update position as the first starting point position. As you can see right now in this line, you are using this position coming from this line, which was the first point right here, right? But on the next iterations, you want to use this point as a new pos right here to create a new position, which should be above this point. So to do that, we could update the position with this new position like this, and as a result, at each loop, the new position has been updated with with this one, this position being updated with this new position, and as a result you'll be able to iteratively move this point to this direction that you have just created. And let's also show the vectors, vector as a marker for each point. To do that, we could set the point attrib for b1 at pt, which is a first point in the for each loop. The first point will be this one, second point will be this one, and so on, with the direction that I created. Okay, and as you can see that as a result, you'll be able to see a yellow line forwarding to a point direction, a point position, which you can see that the direction is used to move each of the point to this direction step by step. Okay, now moving, just going upward is a bit too boring, so let's try to make it a bit more interesting. Let's say like creating like a spiral curve. To do that, we could use some simple trigonometry, so let's try to do that. First of all, we can create an angle value with the float. Let's also create a parameter like ang in between 1 and 0 and multiply by $pi and as a result you'll be able to get the value in between 0 to pi, which means in 0 to 180 degrees. Now I'm also going to multiply this by I. So each time the I is increased by 1, the angle will also change starting from 0. And if this value is say 0.1, then I will be incremented by 1, so I multiplied by 0.1 is equal to 0, 0.1, 0.2, and 0.3. So each iteration have different angle to rotate this direction. Now in order to rotate this direction, you can apply cosine angle for x and sine angle for z in order to have a rotational movement. And I'm going to explain a detail about this in different sessions. Okay, so cosine ang and sine ang. Okay, and let's also promote this angle value. And if you increase the value, you can control the size of the rotation like this to make it a bit more interesting. And you can still see that the direction is forwarding to a direct point, which is used, which shows that the point is moved step by step to the next point position. Okay. Now that was the addition and subtraction for the vector. The next thing I would like to show you is the multiplication and division for the vector, which is a bit more easier than addition and subtraction. So let's try to do that. Let's try to see what it does. First of all, I'm going to create a add node with a single point and create a point triangle named as vector multiplication. And let's name the custom vector. Let's create a custom vector. Let's just say 1.0, 0.5, 0.0. And what you want to do now is try to multiply this vector using a float value. Let's create a float parameter, which is from 0 to 1 by promoting this using clicking this one. So you have value in between 0 to 1. And you already see that if you are turning on this marker, you already see that the yellow directional arrow or line is changing its size based on this multiplication value. Now what it's doing is, as you can imagine, scaling a size of the vector. It doesn't really change the direction, but it just changes the size of its direction. So that's what it does. If it's 0, then the size has been multiplied by 0, so it becomes 0. If it's 1, it keeps the original size, and that's just it. pretty easy to understand. Let's also try to see the division as well. Point triangle. And let's say vector division. And this time I'm going to copy these code from the multiplication and paste it right here. Promote this mult value here, and this time I'm going to change this to division instead of multiplication. So if it's 1, it's pretty much the same, but if you make this value close to 0, then the lengths become larger and larger. And that is pretty much the same as the division of the size. So if you try to divide the value with a value less than 1, then you can imagine that the value becomes bigger and bigger, and if it's 0, then it's going to be infinite. And in this case, it just gives you some errors. So that's what it is. So the multiplication is division is pretty much the same concept. It's used when you are doing the calculation between vectors and float for multiplication, or a division with the float values. It means to change the size of the vector, not the direction itself. Now let's try to use this multiplication or division in practice, how we can actually use this in terms of geometrical modification with VEX and Houdini. I'm going to start by creating a sphere, and first try is to just try to control the scale of the point, each of the point, using multiplication, which is going to be really easy to do. And first I'm going to create the point wrangle. Now let's name this scale 1 and connect with the sphere. And first of all, let's create a parameter named as scale. Let's promote this, and currently the value is a bit between 0 to 1. Now I want to use this value in order to control the scale of the whole geometry. To do that, we can access to each of the point, and each of the point is indeed expressed as a vector. So what we can do is to multiply each of the vector value with this float scale value to control the scale of each of the point. And luckily, the point of this sphere, each of the point of the sphere can be described as a vector starting from a 0, 0, 0, and the center of the sphere is also 0, 0, 0. So what we could have as a result is the scale of this sphere goes to a center using the center as a scaling axis, a starting point, a center point for the scaling, like this. So it's pretty straightforward, but you do this process a lot of times when in real practices. So remember how you can do this. Now next example is a bit more complex, but still pretty easy to understand. The next thing I would like to show is consider when the sphere is not on a 0, 0, 0 position, but outside the 0, 0 position, somewhere around here, say. And in that case, how can we scale this sphere using this position as a center point of the scale? So let's try to see how we do that. First of all, we want to move this sphere to somewhere else. To do that, I'm going to create a add node, which I can control the coordinate by myself. Let's just move it to the random direction, somewhere around here. Okay, and let's use copy to point node to move the sphere to that direction. Then let's try to scale the sphere using a scaling calculation like we did right here. So if we try to use the same calculation to the moved sphere, what we get as a result by moving the scale slider, it just shifts. The sphere does change its size, but what it does is shifting its center to the origin of the space to 0, 0, 0. So that's not really what we want. We want to scale this sphere using the center of the sphere as the center of the scaling. So let's see how we could do this. Now let's try to draw what we want to do now. So we have sphere somewhere which is off the 0, 0 position, and we want to scale the sphere using the center of the sphere, not like this. Okay, so let's think how we can do this. So to scale up the sphere, first thing we need to do is to access each of the point of the sphere, which is pretty easy to do. We just need to access to the point attribute of the sphere, right? Now next thing you want to do is to calculate the scale, but if you try to just scale each of the point at this moment, currently the position, it can be thought like a vector value going from 0 to this position. So if you do a scaling for this vector, you are just changing the size of this vector, like smaller or bigger. So that's the reason why the sphere is moving toward the origin or going outward like this if you scale it up. So the key is to first move the whole points so that the center of the sphere comes to this position, the origin first. Then in this case, all these vectors for each the point on the surface on the sphere will have a vector like this. So using those vectors, you'll be able to calculate the scale, which is using the center of the origin of the space as the center of the sphere. And after you have calculated the scale, you can move the position back to the original position so that you can keep the original center position, and at the same time you can also change the scale of the sphere. Okay, so there's 3 steps you need. First step, move the sphere to the center, the origin. And second, scale. Then 3, move back to the original center positions. So that's the 3 steps you need to do in order to scale a geometry which is outside the origin. So let's try to do this. So in this case, we need to move the sphere to the origin, which is the corresponding to the center of this sphere, the original sphere positions. So we need to move this sphere back to this position somehow. And in order to do that, we need to have a center point of this sphere first, and we can actually get that by accessing to this point, which is the center of this sphere. So let's try to use this point to move this sphere back to the origin. Okay, so we're going to connect this point to the second input, and then first of all we need to access to its point position from the second input. Let's name this Sen, point, second input, P0. Okay, and before we're going to scale, as I said, we want to move this geometry back to the origin, and in order to do that we can do the subtraction using the central point position. So by doing the subtraction, since this is the point position that I have got, and from the center to a point position is actually a vector, and by using a negative direction, the negative value of this vector, which goes from the point to the center, we'll be able to move all the geometry back to the center. So we can subtract the current point position of the sphere with this center value. Now we have just moved the sphere back to the center, then we can scale the value using the origin as a scaling point, scaling center. Now after we have scaled it, we can move this back to the original point position by adding a center again, like this. And as a result, combining all those three transformations, you can create a scaling function which works in the very positions like this. So this idea is pretty important when it comes to deal with the transformation in terms of translation, scaling, and later on, not in this session but in a bit more advanced sessions, for vectors we're going to deal with the rotation as well, and for the rotation it is also important to think like this way, considering where the axis is for the scaling or rotation. Okay, and moving back to the center is a pretty necessary idea, pretty important idea when it comes to transformation. So please do remember this. Okay. The next thing I would like to talk about is to retrieve some basic information out of the vector. One is the normalized direction, and one is the magnitude of the vector. Okay. So first I'm going to create an add node with the single point, and let's create a point wrangle. Connect it with this add node, and let's name this vector normalize. So when people say normalized vector, or when one say normalized vector, it means is that the vector is only considered as a direction and not the size. The size is always 1 when you are using the normalized vector. So the only consideration you can think of for those normalized vector is just the direction. And you can actually get this normalized vector out of any vectors using a function called normalize. So let's try to do this. So vector v1 is equal to some random vector value like this, and let's create an attribute called v1, apply stored with this v1 attribute value, and for a let's try to visualize this first. So it looks like this right now. Now if you look at the geometry spreadsheet, you can check the vector itself right here. Now currently the vector has the both information, one is the direction and one is the size, and because x and y and z is more than 1, the magnitude or the size of the vector is, I guess it's more than 1 for sure. So, and if you only want to retrieve the directional value out of this v1, then the good idea is to use the to retrieve the normalized vector, so that the length is always going to be equal to 1. But the direction is always stays at the same direction. And to create that, we can do that by using a function called normalize. So we're going to create a normalized value for a v1 and apply to a v2 attribute and see the difference. And as a result, you'll be able to see a vector on top of a yellow one, a cyan vector is being created, and this is the actual vector, which is the size of 1. So this is the normalized vector of a v1. And if you only need an information like direction, using keeping a habit to normalize the vector at always is a pretty important thing to do, I think. Because in some cases, if you don't use normalize for a vector operation, sometimes it gives you a weird errors, like for cross product or dot product that I'm going to show you next. Okay, so if you only need a directional value, try to normalize as much as possible. Now if you do need a size, then that's fine without the normalization, like for translation and so on. Now I have told you that you can normalize the vector, but there's also a way to retrieve the current size of the vector, so let's also try to see how we can do this. Okay, so I'm going to copy this one and change this to vector magnitude. And I say magnitude because there's many ways to call the size of the vector. Sometimes it says it is called as the length, sometimes it's called as size, sometimes it's called as magnitude in different contexts. But everything is just the same meaning. It's just the size of or length of the vector. Okay. To get that, what you can do is to use, let's create a float attribute called mag1 for a v1. You can retrieve the length of the vector by using the function called length, and inside the parameter you can just declare a vector value that you want to calculate the length, like this. Okay, and go to the geometry spreadsheet to go for a mag1, and you'll be able to see the actual size of the vector for this yellow line, yellow direction. Let's also check the size of this v2 to see if it's really equal to 1. So be at v2. So I have just created the mag2 attribute and storing this length for the v2, which has been normalized from v1. Let's see. And the mag2 is equal to 1.0, so as I told you, the size of the normalized vector is always 1. Now since these are really essential and pretty easy to understand, you might not need to have any exercise for it, but let's try to do some simple exercise for this as well. Okay, so first of all, I'm going to create a sphere geometry, making it as a polygon so that we have vertices like this. And what I want to do is to create some normal directional vector for each of the point, which goes from the center to outward. And I also would like to create it as a v1 and use that v1 vector to move each of the point to that direction. Okay, and at the same time I also want to try to use the normalized vector of that random vector to see the difference. Okay, so one point you use random values, one point you use a normalized vector, meaning the size equal to 1, and see the difference. Okay, so point, I'm going to create a point wrangle. Let's say init, and I'm going to first create a random float value. Let's call it rand, and rand using @p as a seed value, and create a v1 attribute as a vector from using a point position of the sphere multiplied by a random value. As a result, you'll be able to get this kind of a normal directional vector as a v1, but has different sizes at each position. Okay. Now I would like to use this vector value in order to move the point using this vector. Okay, for each of the point on the surface. Okay, so point wrangle, and let's say move with normal. Okay, so first of all, I'm going to retrieve the value v1 from the attribute. So vector v1 is equal to b at v1. Okay, and I'm going to try to move the point position by adding a v1 value. Well, I'll just say v, since there is only one value. Okay, then maybe multiply by some multiplier as well. Okay, multiply, and if I say 1, then the point slowly grows up. Each of the points slowly grows up randomly with the different sizes, because each of the vector has different size. Okay, and I would like to switch this between the normalized vector as well. So if I do some switching, I would like to normalize this vector v with some toggle UI. So let's say if chi use normalize is equal to 1, then normalize this vector v and update it to v value. Okay, I think I have some error here. Okay, I need to close the parentheses here. Now I also need the parameter for use normals. Let's make this toggle. Go to the edit parameter interface and click this one and change the type to a toggle so that you can use a checkbox for on and off. If it's off, it's 0. If it's on, it's 1. If I click here, the vector has been normalized and all the size of the normal become 1, so the scaling or the moving of the point, the translation value for each point has become all the same from 0 to 1. If it's off, then it's using the random value like this. So you can see the difference what's without the normal and with the normal like this. So it was just a small exercise for testing the normalize. Okay, now let's do this and let's go to the next one. The next thing I would like to talk about is a bit more advanced topic for a vector, even if it's a basics topic, is a dot product of a vector. So let's try to see what dot product is. First of all, dot product is the calculation method for two vectors. Let's say we have two vectors A and B, like this. And the dot product is written in mathematical terms like this, A dot E. So this is the dot product. Okay. And the result of dot product of two vectors is always a float value or a number value. And this number value is actually a projected size of two vectors. For two vectors. What I mean by projected length, in this case, you project one of the vectors to other vectors. For example, if you project this v to A perpendicularly, it goes like this, perpendicular, and you get this size here, and this size is the dot product you will get as a result of this calculation. It's the same for A to B. If you project A to B, you get this projection, and this length is also equal to F, so that is equivalent. It's the same value. So the projected value is the dot product result. So if the length of both A and B is the same and aiming at the same direction like this, then if you project A to B, then it goes like this, directly goes to this. So the length is equal to, let's say if the original length of A and B is equal to L, then the dot product is also L. If B is longer, let's say 2L, then, but if it's still parallel, then the length, the dot product of A and B is still L, because it's A is projected on the longer one, like this. So that's how the dot product works. Now, what if the A goes to this direction and B goes to this direction? Now in this case, the projection goes like this. If you want to project B to A, you extend A to the negative direction, then project like this. And as a result, you get this value F, but this F value is a negative value. If the projected point right here is in the range of this A vector from 0 position, then it's positive. But if it's on the negative direction, then the output dot product result will be negative as well. So that's the thing you want to remember here. Okay, and if A is facing at one direction and B is facing out the opposite direction, then if you project, the value is equal to and let's say that both sides is L, then the F is equal to minus L. So that's how it works. Now there is one more chord condition that you might want to remember. When the A is in one direction, the B is on the perpendicular direction like this. Now in this case, if you project one of the point on the B, on the end of point of the B to A, the size of F is equal to 0. So that means the dot product is also equal to 0. So you can use this dot product to check if the angle between A and B is in 90 degrees or perpendicular, or in the same direction, or is in the positive direction, or on the negative direction. So the information of this dot product is pretty useful for many cases, and I would like to show you an example as well. So first of all, let's try to use this dot product in Houdini with the VEX to see how it works. I'm going to add another add point, add node with a single point, and going to create a point wrangle. Let's name this dot product 1. Okay, and let's create two vectors. One is a simple vector, which is the x directional vector, so say set 1.0, 0.0, 0.0, like this. And for a v2, I'm going to create a vector where the x is parameterized as x, which you can control with the parameters, and y equal to 1 and z equal to 0. And let's have this as an attribute so that you can visualize it. Okay, now let's first visualize how it looks like. So the yellow one is the v1 and the cyan one is the v2. Okay, now let's also promote the parameter x, and by controlling it, you'll be able to control the x from left to center. Now let's also change the range of this x so that it goes from -1 to 1. Alright, so that the angle of the vector goes from left to right, left to right. Okay, now what I want to do is to calculate the dot product between those two vectors and see what's the result of this value. And currently the size of this size of this yellow line is equal to 1. That is because x from 1, and the size of this v2 is not known for now because I'm changing the x value like this. Okay, now let's try to calculate the dot product using a dot function in Houdini. So in order to do that, first create a variable for float and use dot function, and in order to use it, you put two vectors inside as a parameter. The first one is the v1, second one is the v2, and as a result you'll be able to calculate the dot product between two vectors. And let's show this as a text marker this time. So I'm going to store this in an attribute called dot. And currently we don't have any marker for this dot flow value, so let's create one. Going into the visualization, right click, click plus, marker, and let's name dot dot dot. Okay, and let's also make the text a bit bigger, opening the display option by pressing D, and then going into the guide font, large. Okay, now you see the text right here, and this text right here showing right now is the dot product value that I have just created. And by changing the sliders, you should be able to change the value of this dot product. And currently, as you can see, it is equivalent to this x value that I have right here. That is because as I said, the dot product is the projected lengths of between two vectors, and currently let's say this is the base vector v1 and this is the vector that you want to project, and this is the point that you're going to project onto this yellow one perpendicularly. And the x coordinate of this point is this value itself, x, and the y value is 1. So if this is x value, if this v1 value is on top of the x axis, then the projected value should always be equal to this x value right here. So that's why you're getting the same result, the same number that I have written here from this slider value. And as you can see, if the x is equal to 0, then the value is 0. If it's x is equal to -1, it's -1, and +1 is +1. Okay, so let's try to change this second vector's orientation a bit more complex to see it a bit more to see it with the more complex situations. So what I want to do now is to rotate this vector 2 line like this, and to see the difference of the dot product values. Okay, so I'm going to copy this point angle and try to change some values for v2. Now in order to create the rotation of the vectors, I'm again going to use a trigonometry. So to do that, we need an angle value first. So I'm going to create an angle value with a CHF and multiply by pi multiplied by 2. So in this case, you'll be able to have a value in between 0 to 2 pi with this angle value, which is in range between 0 to 1. Meaning you have a rotational angle value between 0 to 360 degrees. Okay, now I want to use this angle with the trigonometry. So for the x, I'm going to say sine ang, and for the y value, I'm going to say sine ang and keep dz as 0. Now let's promote this angle value. Now let's change this rotation value, and you'll be able to see that the vector is rotating from 0 to 360 degrees. And let's see the changes of this dot product value. Now it's using angle, so the value is not equivalent to this one, but based on the position of this vector, you can see when it is positive and when it is negative. If the direction is on this side, the value is always positive. If the vector is this side is the negative side, then the value become negative. Then go positive again and becomes 1 if it's facing on the same direction. If it's perpendicular, like to 0.25, it's pretty much close to 0. Become positive, negative, and so on. So this value between two values is pretty useful when it comes to define several things, like whether the point is inside some geometry or not, or something like that, or if all two vectors are facing at the same direction or not, and so on. So try to remember about this feature, this useful feature for later usage. Now we're actually going to use this dot product to check if the certain point is inside the geometry or not, using this dot product, and that is pretty easy to do actually, and I'll show you how you can do this. Now I'm going to create a point to check whether this point is inside or not, inside the geometry or not. So this will be the point that I want to check, which I'm later going to move with these point value parameter. And I'm going to create a sphere as a geometry which I want to check with. Okay, like this one. And in order to calculate a dot product, I need to have a normal directional point value for each of the point normal direction for each of the point. So I'm going to create a normal direction using normal node and set it to normal. Point like this, so that if I click this one, I'll be able to see the direction of the normal like this. Alright, now let's check if the point is inside, this point is inside the sphere or not. Now in order to see that there's a point inside, I'm going to make this view wireframe. Okay, now I am going to make this positive, and I'm going to create a point wrangle and connect this point that I want to check to the first input of the point wrangle and put this geometry the second input. And let's name this check inside with dot. Okay, now what I want to do, first of all, what I want to do is to retrieve the closest point from this point inside the geometry or outside the geometry, and get the closest point to the surface. that I want to check. So in this case, the closest point might be somewhere around here. So I want to get that value in order to retrieve the normal direction of that point. And also I want to retrieve the direction value from this point to the nearest point of the surface. Okay, so I can get the nearest point position by using a function called near point from the second geometry with a current point position. And as a result, you'll be able to get a point number for that point that I want to retrieve. Now from that point number, I will be able to retrieve like an attribute like point position and normals. So let's retrieve that. First of all, a position, you can use point function from second, input with the p attribute at npt. Let's also get normal using point second input normal npt, like this. Now first of all, let's try to store two vector values into this point v1 as a b1 and b2, and b1 will going to be a vector from the current point to the nearest point position. So for that, you can calculate the subtraction as I explained previously. So in order to create a vector between this point and this point, you just need to do the subtraction from this point to this point. And this point position is retrieved as npos. So the direction that you want to create is npos minus at p. Okay, now let's draw this as v1. Okay, now you get this vector direction like this, from current point to the nearest point position on the surface. Now the next thing I would like to get is the normal directional value on that point, this direction. And I want to retrieve that normal direction, which I've already done here, and store that to a v2 attribute for the current point for this one. So let's do that. V at v2 is equal to n norm, like this. Now it's not really in the same direction, but it's pretty close the direction which is it aiming for. And if I change the position of this point, it slowly changes the nearest point as well. So most of the cases, the direction between the point and the normal doesn't really match, but it's pretty close to each other. So the next thing I would like to do here is to calculate the dot product of these two vectors and try to see what the number is, and try to use that value in order to determine if the point is inside the sphere or not. Let's see how we can do that. Okay, so first of all, I'm going to calculate the dot product between two values. So float val is equal to the dot. Now direction is the first vector and the known is the second vector that I want to calculate the dot product with. And let's have that as an attribute as a dot. And here's the number that you get as a dot product result. Now keep focus on this number for a while, and while I move the point from inside to outside and see how the number changes. Now currently the point is inside the sphere, and if I move this value bigger, and as soon as it goes outside, you see that the value became negative. That is because the two vectors, this yellow vector and the cyan vectors, are facing the opposite side. So that's the projected value of one of the vectors becomes negative, so the result of this dot product becomes negative as well. And also you can see that the point is outside the sphere as well. So you can kind of guess that if this dot product of the normal and the nearest point direction is negative, then the point is outside, and if it's positive, you can guess that the point is inside the sphere. So that's one of the tricks you can use in order to computationally determine whether the point is inside the geometry or not. And it doesn't have to be sphere, it could be any kind of geometry which has been remeshed like this, which has a point normal directional values on each point. Alright, so let's finish this up by setting the color when the point is inside and outside. So if the value is positive, then the point is inside. So let's set the color of this point as red. So if it's outside, let's set the color of this point as blue. Okay, and oops, curly bracket, and let's create some small sphere like the size of 0.05 and copy the sphere to this point. Now let's make this back to a shaded and showing the sphere as a wireframe, and try to move the point and see if the point color changes dependent on the point is inside the sphere or not. Right? I think it works just great. So this is one of the really useful practical usage for dot product. There are a lot more things you can do with dot product. I'll show you later with some more advanced techniques. But in this basic sessions, this is one of the way you use a lot for dot product. Okay. The last thing I would like to talk about for a basic of vector is cross product. The cross vector also works with two vectors, but the result you get is a vector instead of float values. Let's see what it does. Now you have to think about this in 3D space. Say you have vector A and you have vector V. And the cross product of these two vectors is actually a perpendicular vector to both of those vectors, which is vector C. So perpendicular to both of the vector means that the C is perpendicular to A, but also perpendicular to B as well. So you see like this kind of vectors. This is vector A, this is vector B, and this is vector C. Like this one. So you have 90 degrees vectors for this is, if this is C, you have 90 degrees between B and C and 90 degrees between C and A. So that's the result you get when you calculate the cross product between A and B. Actually, there's more to this cross product for information like the size, but for now, as a basic property, the direction of the vector that you have been created between A and B is perpendicular to both of the vectors. So that's the most important part of this cross product that you want to remember for basic stuff. So let's try to remember this property first and try to use this by keeping that in mind. Now let's add another point using add node. Okay, and let's create a point wrangle. Let's name this cross product. Okay. and create a two vectors like we did for the dot product. B1 for set 1.0, 0.0, 0.0, vector 2, B2 for set say 0.0, 1.0, and we're going to set z as a parameter and set b1, b2 as a attribute so that we can visualize it with a marker. Okay. Now let's also promote the z value, z parameter here that we have written with the chf function. By changing this value, I can change the z coordinate of this vectors. Now let's also make it in between -1 to 1 as well. Like this. Right. Okay, now let's try to calculate a cross product between those two vectors and see what kind of vectors we get out of these two vectors. Right, so the output of the cross vector is vectors, so I'm gonna create the vector variable named as val is equal to cross b at b1, b at b2, and store that as b3 attribute. B3 equal to val. Okay, so I have just created the new vector 3 has been created, and this red vector is the actual cross vector result, the result of the cross vector. And as you can see, it is perpendicular to both the yellow one and the blue one. If I change this value for the z, you can see that the red is following the cyan one and the yellow one to keep the angle between those two angles always being perpendicular. Okay, let's also try to change the x value as well. So chf x, and let's make this -1 to 1 as well. Okay, if I set x, in this case, if I change x to -1 to 1, the red one doesn't really change. That is because even if I change this x1, the x remains the same. That is because it is still the angle between the red one and the cyan one is kept as perpendicular even if I change this x value. Only when I change this z value, the red one follows the cyan to make it preserve the perpendicularness. Like this. So that's the important property of the cross product. Now let's also try with a bit more complex vector, like we did for the dot product. I'm going to copy this one and create a rotational base vectors for the second one. Okay, so I am going to create an angle with the chf ang multiply by pi multiply by 2, and replace this v2 with 0 cosine ang sine ang. Okay, and let's see how it goes. Okay, it should be 0 and show up the angle value, and let's also delete the x and z value, which I don't need anymore. Now if I change this angle, I'm rotating this vector 2 angle, vector 2 vectors, and related to that, the red one also rotates to keep the angle between the red one and cyan and red one and yellow being perpendicular, meaning 90 degrees. Like this. So This cross product is also pretty important when it comes to use it for something like orientation or rotation, like using this for axis for the rotation and so on. So the actual practical usage is going to be a bit more advanced, so I would like to keep it for later sessions, but I'm going to show you a simple example how we could use this to make it for alignment for orientation as a simple case. Okay, so let's do this. First of all, I'm going to create a sphere. With a primitive or a polygon. Let's also change this to shaded, YU is shaded, and create a normal node. Set it as a point so that you have a point normals at each point. And the first thing I would like to do is to try to move the box on top of each of the point with this normal information to see how the box is being oriented. So I've just created a box and use copy to points. So currently each of the point has a normal information at each point. If you go to geometry spreadsheet, you have this normal information called n at each point on the sphere. Now by having this normal vectors, you'll be able to change the orientation of the box using copy to points, and let's see how it works. And let's set the size for the box a bit smaller, like this. So it does seems like the box has been cleanly oriented on top of a point. Each of the face is facing toward the outward direction. Now, but there is one more attribute you can use to control the orientation of the boxes or geometry when you use the copy to point node, and that is up vector. Together with the normal vector, using up vector, you'll be able to control one more axis for the orientation. And let's try to create that up vector using cross vector, which is perpendicular to a normal vector, and see what happens. Okay, so first I'm going to create a point wrangle. Let's focus this for now, and I'm going to name this cross vector. And first of all, let's retrieve a vector value normal, and I'm gonna call that v2. So v2 is at n, and I'm going to store that v2 attribute to v at v2. Okay, and oops, v2 is equal to v2, like this. So we have currently a normal direction like this. Now I also want to create another vector, which in order to calculate a cross product between this normal vector, and that vector could be any vector. I'm going to just create some initial vector created by myself, something like name this as v1 and set 0 1 0, so it's like a y directional value going upward. And apply that as a v1 attribute, so like this. So at each point you have the yellow line and the cyan line. The yellow one is the v1 and the yellow one is cyan one is the v2. And what you want to do is to calculate the cross product between those two vectors to calculate the perpendicular vector for two vectors and see what it looks like, how it looks like. So let's name the output as cross v and use cross product. between v1 and v2 and store this value to v3 attribute like this. Now you get this kind of vector, which seems like a turbulence-like rotating vector, which seems to be a tangent vector of this sphere, and the direction seems really constant. It's rotating around the center. And let's try to apply this to an up vector of this geometry and see the difference with the orientation, how the orientation changes. So I'm updating the up vector with this v at v3, or maybe cross v. Okay, and go back to the box and hide the marker and look at the box orientation. And you might have noticed some changes here. The orientation have changed from previous one to the next one using the cross vectors. Now let's try to see the difference by creating some switch. If chi use cross is equal to 1, then update the up vector with cross vector and promote the parameter. Go to the edit parameter interface and click this one and change this to a toggle, so that if I turn this on, it's using the cross vector as an up vector. If not, it's not. So right now it's not using a cross vector, so the orientation looks like this. If I click this cross vector, the orientation changes to make the orientation of the box a bit more organized than before. So this is one of the tricks you can also use in order to control the orientation for the cross vectors, cross products. Same for dot product. The cross product has many usage for many purposes, but this is just one of the simple usage, and I would like to show what you can do with it for more advanced usage in later videos. But in this basic sessions, I just wanted to show you the most important aspect of the cross product and the dot product. And this is the one to get the perpendicular direction, to use it something for orientation. So now this is it for today. We have learned the basics of vectors, the operations, addition, multiplication, division, subtraction, and dot product and cross product with some examples. I hope you understand a bit how you can use the vectors, what's those dot and cross vectors for. So this was the basics of vectors that I have taught you today, and there are a lot more things to teach you about the vectors, which I haven't told you yet. But before getting into that, we need to learn other stuff beforehand in order to understand more of those advanced topic. So the next topic that I'm going to talk about for next week is trigonometry, like cosine, sine, and tangent. What it is, how you can use it with the examples. And we have already used it with many examples, but we're gonna get in depth what really is and how you can really use it for practices. Okay, so please look forward to it, and thank you all for watching today's video. And I have also started a Patreon myself. If you feel like you could support me, please do. I'll really appreciate it. And if you like the video, please like and subscribe. Okay, so see you next time. Thank you.